Okay, here's a quick review on how to determine the structure of an ester from a proton NMR. So, first, if we have an ester, the ester will have two parts. It will have an alcohol part, and it will have the part that came from the carboxylic acid. And there's two key chemical shift regions that we look for to assign the groups at the beginning of each one of these parts. The hydrogen attached to the carbon attached to the oxygen is going to be between 4 and 5 parts per million. So we want to look for that group because that will be the group that was attached to the alcohol and now is attached to the alcohol part of the ester. The hydrogen attached to the carbon next to the carbonyl, that hydrogen will show up at roughly about 2 parts per million, probably in the neighborhood of about 2.2 or so parts per million. So between 2 and 2.2 parts per million, somewhere in that neighborhood. And so when we're going to measure, or when we're going to use our structure to determine, our NMR spectrum to determine the structure of the ester, we're going to follow the same general rules that we would always follow, but those are the two key sets of resonances that we want to look for. So here's an example of an ester NMR. So let's try and figure out what it is. The first step is to determine the integrations for each proton. That gives us the type of group for that resonance, meaning is it a CH, is it a CH2, is it a CH3. Then we'll look at the assembling the pieces. We'll assemble the pieces from the integrations, and then we're going to put the pieces together and then we're going to attach the pieces using the chemical shift information and also the splitting patterns. Okay, so let's deal first with integrations. So the integrations are represented in this spectrum by the distance between the integration marks for each resonance. So what you have to do is get a ruler and you have to measure each one of those in centimeters. So this one is 0.8 centimeters. The triplets integration is 1.5 centimeters. Now, for the next one, there is this multiplet and the doublet. The multiplet goes to here, and then the doublet goes from this resonance up to this one. So we're going to have to measure those two separately. I get about 1.2 centimeters here, and I think I get about 4.5 here. And now finally this triplet is roughly about 2.3 3 or so centimeters. So you have to measure that with a ruler, and that gives you the distances, and these all represent the areas underneath the peaks, which is a representation of the number of hydrogens. But now what we have to do is now we have to divide each one of these numbers by the smallest distance to get the ratio. So what I'd really like to get now is I'd like to get the ratio. So I'm going to divide each one of these by 0.8 because that's the smallest value. And that's going to give me an estimate of the number of hydrogens in that group. So 0.8 divided by 0.8 would be 1 hydrogen. 1.5 divided by 0.8 is about 1.875, so I'm going to call it 1.9. 1.2 divided by 0.8 is 1.5. So this is 1.5. Again, these are the ratios. 4.5 divided by 0.8 is 5.6. And 2.3 divided by 0.8 is about 2.9. So there's my ratios. Now what we usually do is round up or down to give us the whole number of hydrogens that each peak represents. So 1.9 is going to say there are 2 hydrogens. There's 2 hydrogens are represented by that group. 1.5, I don't know what to do with 1.5, so I'm going to say it's either a CH or a CH2. 5.6 rounded up would be basically 6 hydrogens. We can't have a carbon with 6 hydrogens. I'm going to guess that this is probably 2 CH3 groups. And then 2.9, that's going to be 3 hydrogens. This was 6 hydrogens. So now when we have 3 hydrogens, 6 hydrogens, 1.5 hydrogens, 2 hydrogens, and 1, let's make groups out of that. So 3 hydrogens would correspond to this is a CH3 group. The 6 hydrogens, got to kind of a little bit ahead of myself, 6 hydrogens would be most likely 2 CH3 groups. I don't know if 1.5 represents a CH or a CH2. That'll become apparent as I solve the structure. 1.9 hydrogens is definitely going to be 2 hydrogens. That's going to be a CH2 group. And then the 1 hydrogen at the end. Okay, so now what I've done is I've determined the pieces that I have from the integration. So I'm going to move ahead here and get a clean spectrum to work with so that I can basically say this is now 1 hydrogen, this is 2 hydrogens, this is either a CH or CH2, I don't know that. This is definitely a CH2, this is a CH. This doublet is most likely 2 CH3s since it added up to a 6. And this is most likely a CH3 since it had 3 hydrogens. Right, so this will make it a little cleaner for us. Remember, this was 1.5 hydrogens and I didn't know what to do with it. Okay. So here's our pieces. So I've got a CH, a CH2, CH or CH2 for this multiplet right here. The doublet is 2 CH3s, and then this triplet is a CH3 group. So remember, this is an ester. So there's my ester structure. What did we say earlier? We said that the group that's attached to the oxygen is going to show up between 4 and 5 parts per million. In this case, what kind of group is that? It's a CH. that's attached to two other things. So if I call this proton A, that's going to be A. The group that was a little bit better, a little bit greater than 2, is going to be the one that's attached to the carbonyl. That's the CH2 group. That's this one, so we'll call that B. Okay. So those we said were characteristic resonances of esters, groups that are attached to the oxygen, groups that are attached to the carbonyl. Now the rest of the pieces have to go on this structure. And this is where I'm going to use the splitting patterns to determine my connectivities. So, remember that a single peak means you have 0 neighbors. A doublet means you have 1 neighbor. A triplet means that you have 2 neighbors. The quartet means that you have 3. And where did these come from? It came from the n+1 rule, where n is the number of neighboring hydrogens. That gives you the number of peaks. So we just basically reverse and solve for the number of neighbors from the number of peaks. So it's number of peaks minus 1. What if you have something like this, or something like this? That's a multiplet. And multiplets are groups that are in between. So if you have a carbon group in between, let's say, a methyl and an ethyl, these groups, that will be a multiplet, because it'll see a quartet here, it'll see a doublet there, so it actually would be a doublet of quartets or a quartet of doublets. It's just a multiplet that's not a singlet, a doublet, a triplet, or a quartet. So that means that A is in between 2 groups. Well, we already know that. We know we've got to have groups here and here for A. And for this multiplet, it's going to be in between as well. Okay. So, what's the next thing that we could look at? Well, let's look at this CH2. Let's look at B. It's a triplet. What's it next to? It's next to another CH2 group. Now remember, we didn't know whether this group right here was a CH or a CH2. That's basically all I have left. So the CH2B that I have right here, because it's a triplet, it means it's next to another CH2 group. So that definitely makes this group a CH2, and C, it makes that group. This being a multiplet means that it has to be in between groups, and it will, because we need to put a group there. Okay. So I've assigned this group, I've assigned this group, I've assigned this group, and what do I have left? 2 methyls that are a doublet. So the fact that these 2 methyl groups, these 6 hydrogens, are all equivalent to each other means that they're attached to the same hydrogen, or they're symmetrically equivalent, or both. And so in this case, these 2 methyl groups must be attached to the same group. And since it's a doublet, how many CHs is it next to? Well, it's next to 1 CH, because it has 1 neighbor. It's a doublet, it has 1 neighbor, that means it's next to a CH. So those 2 methyl groups I would call D, and so there's D and there's D. Now I've got one more group left, one CH3, which will go there. What's that CH3 next to? It's a triplet. That means it's next to a CH2. Voila, it's next to a CH2. So we can call that E. And now I'm out of groups, so now I've made my assignment. So now what we want to do is we just want to double check and make sure everything matches up. So for carbon A, it's at 4 to 5 parts per million, which means it's next to an oxygen. It's a multiplet, which means it's in between two groups, and its integration is 1, so it's a CH. It's attached to two equivalent CH3s, so that's these. They have an integration of 6. They're equivalent. They have as neighbors 1 hydrogen, which they do, so that matches up. For B, it's at 2 something parts per million here, 2.3. That's about where it should be, or that is where it should be for next to a carbonyl. It's next to a CH2 group, which it is. That CH2 group is this one. It's a multiplet, meaning it's in between two groups, and in this case its integration was 1.5. Could have gone either way, but we know we have no choice. It has to be a CH2 group. And then that CH2 group has to be next to this methyl group. This methyl group now has a triplet. It's next to the CH2. And so everything makes sense, and so most likely the structure's right. Last thing that I'll add, and I'll go back to this slide, is that if you look at the chemical shift region, around 1 part per million is where you always have the CH3 groups in a proton spectrum. So I didn't say that from the beginning. But when you look at a proton spectrum, these groups down in here are typically your CH3s. Okay? So that's how we would determine the structure of an ester from scratch.